the last part of the chapter is about population parameters inferences. Okay, we were dealing with the means. Now we are dealing with the proportion. Proportion is pretty easy because we're going to use what? The standard normal distribution that we already know, so we do not have to calculate degrees of freedom or nothing like that. So we have the two populations and the two samples. From this sample I have P1 bar, from this sample I have P2 bar, and we are going to establish the same thing as the hypothesis testing and the confidence intervals. So for the confidence interval is P1 bar minus P2 bar plus or minus E of alpha divided by 2 times the what? The standard deviation, that is P1 bar times 1 minus P1 bar divided by N1 plus P2 bar times 1 minus P2 bar divided by N2. That's it. That's for the confidence interval. And for the hypothesis testing, we have the same situation. P1 minus P2 is equal to 0. Again, it's not equal to 0. Greater or equal versus less than equal than 0. And less or equal greater than 0. In this case, we have a two-tailed test. In this case, we have a lower tail test. And in this case, we have an upper tail test. And we are going to use the standard normal distribution for the critical values, and then we need to compute the test value. Now, we have a little bit of complication over here because we need to calculate, if we are dealing, for example, with the P, with the same proportion in both populations, we have to calculate a pooled sample proportion. Okay? So that pooled sample proportion, we have the formula, so it's nothing really complicated. Plus P2 bar times N2 times N1 plus N2. This is the pool sample proportion for the two samples, and we are going to use this one in the test. The test is equal then going to be P1 bar minus P2 bar divided by what? Minus 0, of course, if we are dealing with zeros, but it can be any number. Divided by what? The square root of my pooled, okay, my pooled proportion times 1 minus P bar times 1 over N1 plus 1 over N2. Okay? That's it. That's it. I mean, that's so simple to make this. Okay. Let's do a problem so we can understand better these situations. So what is difficult in this chapter, it may be that we are dealing with both confidence interval and hypothesis testing at the same time. And when we are dealing with hypothesis testing, we need to check if we are dealing with a two-tailed test or a one-tailed test, upper or lower. And in confidence interval is always the confidence interval, and we need to establish this alpha divided by 2 situation. Okay, so let's do one problem that involves both hypothesis testing and confidence interval. So let's do problem 33. 33 is about the two airports that are the busiest airports in the United States is O'Hare in Chicago and the Atlanta airport. And they are leading with congestion, delayed flights in both airports. Okay, flight is considered delayed if it's more than 15 minutes behind schedule. So we have this this data. Chicago and Atlanta. Okay, and we have in Chicago, my sample size is equal to 900, and the delayed departures from those 900 is equal to 252. In Atlanta, we have N2 is equal to 1200, and the delay in Atlanta is 312. Okay, now they don't give us the p-bar, so we have to calculate the p-bar. P1 bar is the proportion of the delayed flights of the total, so it's 252 divided by 900, and P2 bar is equal to 312 divided by 1200, and is the proportion of the delayed flights from the two airports. 252 divided by 900 is equal to 0.28, so the proportion is 0.28, and over here is 0.26. Okay, so really we do have more delayed flights in Chicago than in Atlanta, and that is only for the sample. Okay, state the hypothesis that can be used to determine whether the population proportion of delayed departures differs on the two airports. So we need to know if there is a differences in the two airports. So really, the situation is what? That P1 or P1, not R, P1 minus P2 is equal to 0 against P1 minus P2 is not equal to 0. And that is a what? A two-tailed test. And if we are using the 0.95 confidence level, then this is 1.96 and this is negative 1.96. That's my critical values. This is the test type that I'm using for doing this hypothesis. So state the hypothesis whether they are equal or not equal to 0. What is the point estimate that we have in the proportion of flights that have delayed departure at Chicago? We already have that one. It's 0.28, and for Atlanta it's 0.26. What is the p-value for the hypothesis test? What is your conclusion? In this case, what do we have to do? First of all, we need to calculate the pooled proportion of the samples, and that is equal to what? Go to the formula, N1 P1 plus N2 P2 divided by N1 plus N2, and that is the proportion of the samples, and that is equal to what? N1 is 900 times 0.28 plus 1200 times 0.26 divided by 900 times 1200, and that is equal to what? 900 times 0.28, 1200 times 0.26 divided times 100 1200 times 0.26 divided by 2100. 0.2686. That is my pooled sample proportion, if you will. So I'm going to erase a little bit this in order to calculate the test value. The test value is equal to P1 bar minus P2 bar minus 0 divided by what? By the square root of P times P bar 1 minus P bar times 1 over N1 plus 1 over N2, square root. So P1 bar is 0.28 minus 0.26 divided by P bar is 0.2686 times 0.7314 times 1 over 900 plus 1 over 1200. That is 0.02 divided by what? Let's do it. Let's do it. Let's do it. Something wrong. Oh, I didn't square that. Okay. 1 divided by 900 plus 1 divided by 1200 times 0.7314 times 0.2686 square root x times 102, that is equal to 1. That's equal to 1.023. Okay, so the test value is 0.1023, and the test value, if we compare it with my critical values, is over here. So it's in the non-rejection or the fail to reject zone. So there is no conclusions. There are differences in the delays between Chicago and Atlanta airports. Okay, so do not reject the null hypothesis. And that's it. That's all about chapter 10.